Hi, Kamile. The problem starts with h as a function of p minus h as a function of the initial p. So what's that? That's delta h as a function of p, right? And when you want delta h, you're probably going to get it from an integral of dh, right? Remember that? So where can you get an equation for the integral of dh? Well, you can get a dh from one of two places. You can get a dh from here, h equals u plus pv, or you can get a dh from here, the total differential, dh equals something, you know, this thing that you've been doing for a while. Now, how did I pick the variables here? How do you know that you should do this with p and t rather than p and v or v and t? You know it because in the problem they're saying that p is changing. So, and they're also saying that t is constant. So the fact that p is changing means you want to do it with p. The fact that t is being held constant intentionally means that if you do it with t, then you'll be able to get rid of the t. So that simplifies things quite a bit. Let's proceed with using this total differential equation. The reason why I'm not proceeding by starting with this enthalpy master equation is because I tried that before and I was not successful. So we're gonna keep on going with this. Now on a midterm, how would you choose between the two? I'm not sure. All right, so let's maybe by practice you will get an intuitive idea. I mean, you're quite smart. I think you can do that. So let's get closer here to those. Let's get closer to the solution by doing this. Delta H is equal to, that's an equal sign, delta H is equal to integral of dH, which is equal to the integral of this. I just integrated both sides from here. Okay? So now the problem is I have to get something that means this. I have to find out what this is. And I can find out what that is. Oops, sorry about that. That should be a del. So del H del P at constant t equals, there is a way for me to find out what that is because I have this here. This H is equal to U plus PV. So instead of this H, I'll just put here U plus PV, like that. And this is all at constant t. Okay, so doing that, this is something you've done before, du plus pdv plus vdp, right? You've done this before. And dp goes on all of these. Okay, dp goes on all of these. And these are all at constant t, constant t, constant t, constant t. So immediately, dp over dp is 1, so this is just v by itself. V by itself doesn't care if it's constant t or not because there's no t here. There's no dt or anything like that. There's no derivative here, so the v is just by itself. There's no dp or dv or anything in that term. So to rewrite, this is dh dp at constant t equals du dp at constant t plus p dv dp at constant t plus just a v. Okay, now what's our next step? You determine your next step by seeing what you need in this problem. What you need in the problem, the equation that's given contains an alpha. So you need to get the alpha out of these three terms somehow. But alpha is the isothermal it's the coefficient of thermal expansion. So that means the change in volume as you raise the temperature. So that's alpha. Notice alpha contains a dt, but there is no dt here. This is a dp, this is a dp, this is a dv, this is a du. There is no dt here that I could pull out with math. So I have to turn to chemistry, and notice that there is a du here and there is a dv here. I can use a math trick soon to cause the du and the dv to be du over dv instead of du something or other plus dv. Okay, so next I'm going to use a math trick to get du over dv out of this. And the reason why I want that is because of this formula. The internal pressure, remember that has to do with the attractions between the particles. The internal pressure is equal to, by definition, the change in energy of a substance as you change the volume. So as you increase or decrease the space for the particles, the attractions between the particles will come into play more, and that's the internal pressure. And that happens to be equal to this. Now this contains a dt, notice that. So this is where I'm going to get the dt for my alpha. All right, that's where I'm going to get it. In order to use this dt, I have to have du over dv. So I'm about to use a trick to get du over dv. All right, so here's the trick. du dv times dv dp. So if I put du dv at constant temperature times dv dp at constant temperature, then you could see that really I'm not doing anything because the dv's cancel. This is still du dp, just like it is up here in yellow, du dp. So I haven't really done anything, but I've caused du dv at constant t to appear here in the equation, and now I'm going to take advantage of that soon. So this is plus p dv dp at constant t plus v. Okay, now notice, I'll do this in brown, I can factor out a dv dp here. All right, so I'm going to factor out dv dp. Are you ready for this? All right, so I'm going to bring in another page here, and I'm going to factor out that dv dp. So factoring out that dv dp, let me make sure that I know where I'm starting from. This whole thing was dh dp at constant t, and that equals, I'm going to factor this out now. I'm going to factor out dv dp at constant t, and that was du dv at constant t plus p. There it is, plus v. Okay, so here is the du dv at constant t. Now remember, the du dv at constant t also equals this stuff. Du dv at constant t equals t dp dt constant v minus p, so I'm going to substitute that in for du dv at constant t. So do that in some other color like gray. This is the following: t dp dt at constant v minus p. That's what that is. Whoops, pause the video. Okay, to continue, let me copy down the rest of the equation here, so that I'll copy down the do this in black. Copy down the plus p from there. Copy down the parenthesis here. This was a t, okay. And then constant t dv dp equal sign. Okay, so this was a t here. That was a t. Okay, so I finally have obtained my dt here. So how does that help? That helps because I need the alpha, remember? And these cancel, minus p plus p, those cancel. So to rewrite now, let me just extend this page. Okay, to rewrite, that's del v del p at constant t times dp dt at constant v times t, and then there's plus v. All right, so I have the dt here. Now remember that what I wanted was alpha to be in the equation at the end, and alpha is equal to dv dt at constant p. So I need a dv dt. So here's dv. All right. So here's dv, and here's dt. So hey, can I just cancel these and get dv dt? No, I can't. And why is that? And that's because this is at constant t, while this is at constant v. Remember, previously when I did that math trick, I had to keep, let me go back to that page. Previously when I did that math trick, I had to keep the constant t. So I had it at constant t, and that constant t got copied here, and it got copied here. So that math trick I could do when constant t is preserved. So I cannot do that math trick in this new case. Where is it? Here it is. I cannot do that math trick in this new case because I've got a constant t here and a constant v here, and they're not the same. So I can't combine these into a single dv dt factor. What can I do then? When I have different constant things and different d things, I could use the Euler chain relation. Let's do that. Let's do that in light blue. So -1 equals, now I want a dv and a dp and a d. And now I know you have your own way of doing this, so I'll just do this my way and you can do it your way. We'll end up with the same answer. So let's see, I got dv dp at constant t, so dv dp at constant t is the same as dp dt, times dp, dp dt at constant v times dt dv at constant p. Okay. dv dp at constant t, dp dt at constant v. Okay, so this is the Euler chain relation, and I'm about to use that. So here I've got dv dp at constant t. That was the first factor. dp dt at constant v. That's the second factor. And this third factor I'm gonna put on the other side. So I'm gonna multiply both sides in a darker blue. I'm gonna multiply both sides by the reciprocal of this. So the -1 stays here, and I get dv dt at constant p, constant p equals dv dp at constant t times, I'm just copying this down, dp dt at constant v. So these characters here, these stooges here, dv dp at constant t times dp dt at constant v, those are these guys. So that means because the Euler chain relation, I can just substitute this simple guy in for those. Why would I ever want to do that? I would want to do that because dv dt at constant p is this. It appears in the definition of alpha, and the answer has alpha in it. So that's why I want to put something in there that I could change into alpha. All right, so let's do that. Let me get another page. Okay. Oh, the sun is doing these weird things here, so I hope you could see what I'm doing. All right, so let me go back to this new page here. So this whole issue was dh dp at constant t, and that is equal to, now I'm going to put in this new thing that I've got, maybe just to make sure that I keep track of what I'm doing here. It was -1 times dv dt at constant p, right? And that took care of all this, right? And I just have the t plus v left. Let me put that in there. This is times t, and then that's plus v. Okay, so let's make this page longer now. Okay, so now what I've got here is right. I gotta put the alpha in. So remember, the definition of alpha is 1 over v dv dt at constant p, because alpha is the coefficient of thermal expansion. So as the temperature goes up, the volume goes up. So I have dv dt here. So how can I substitute alpha in? Well, let me solve for dv dt here. So dv dt at constant p is equal to alpha times v, by multiplying the v on both sides, right? So I'm going to put this in for that. So now I have negative alpha V times T, right, plus V. So this is negative, or let me factor out a V here. How about that? I'll factor out a V here. So that's, oh, look, it looks like I'm factoring out a negative V. So that means this is alpha T minus 1. All right? Okay. Now I have the alpha in here, so that's good. And already you could see that what I have here looks like part of the solution that's in the problem, except the minus sign is off. So let me factor out a negative 1 from what I have in parentheses. So I'll factor out a negative 1, so minus V times negative 1. And if I factor out a negative 1 from alpha t, I get negative alpha t, and this is plus 1. And of course, the reason why I did that is because I want this to look like the solution, which has V. The 1 was positive, and the alpha t was negative. So, okay. Notice that this looks like the numerator in the solution. All right, so that's good. Now, let's see here. Okay, so let's go back to what I wanted. What I wanted was, do this in dark blue. Okay, what I wanted from this problem was an expression for delta H. And remember, to get delta H, you integrate dH. And remember, when we use the total differential for for H, the total differential for H, using the variables P and T, we got just one term. Oops. Just one term, and that was dH dP, a constant T, times dP. So this was this was just half of the total differential for H because the dt portion went to 0. All right. So now I'm going to put this in. I'm going to put this in here for the dH dP at constant T. Why? Because this V times 1 minus alpha T equals dH dP at constant T, as we just found. So when I do that, I'll do this, go back to black. When I do that, I get the integral of V times 1 minus alpha T dP. All right? So the delta H here in the problem was not delta H as a function of V. The delta H was H as a function of P minus H as a function of the initial P. So that means I'm going to be integrating from P initial to P final. But V is not something I can just take out of the integral, because this problem didn't say that V is being held constant. This problem said that T is being held constant. So that means V will change with P. So I need to get a formula for V that I can substitute in here. Now, 1 minus alpha T, the problem says that alpha and kappa are constant. So alpha is constant. Our problem also says that T is constant. So this whole parenthetical expression leaves the integral. So I'm going to put it out here. 1 minus alpha T integral Pi to P. Can you see this? Am I getting off the page? All right. Oops. Sorry about that. Okay. Pi P V dP. So V is not something I can just take out, so I need to find a way, I need to find some expression, some function of P that equals V, and I need to stick it in here, okay? I'm going to put a new page out for it. All right. Okay, now where can I get a function of V, that depends on P? Well, notice in the solution, kappa T, the isothermal compressibility, appeared in the solution. That was given in the problem, right? That's the target equation. Do this in green again. So kappa T appeared there. So now let's tackle the kappa T. Why do we choose to tackle the kappa T now? We choose to do that because kappa T contains a function of V that depends on P. Here it is. dV dP at constant temperature. This is the isothermal compressibility. So as you increase the pressure, what happens to the volume? That's the isothermal compressibility, the kappa T. And in this problem, kappa T was constant, so kappa T is a known quantity, check mark. In this problem, T is constant. In this problem, P is changing, so can I solve this for V? Yes, I can solve this for V. Let me solve this for V. Multiply negative V on both sides, so I get negative V kappa T equals del V del P at constant T. Oh, why did I do that? Let me divide both sides by kappa T, negative kappa T. So V is equal to negative 1 over kappa T dV dP. Now, is that useful? Yes, it is. Except I don't want a dV. I just want V. So how can I get rid of the dV? By integrating, of course. So let me integrate this. In order to integrate, I have to separate the variables. All the V's have to be on one side, and all the P's have to be on the other side. So let me do that. Let me get all the V's on one side and all the P's on the other side. I'll multiply. Let me just flip the whole thing. Okay, so this is going to be 1 over V equals negative kappa T dP over dV. I do that because I know the integral of dV over V. So I'll multiply both sides by dV. So dV over V is an integral that I know. You know what that is. It's ln V2 over V1, right? And then the integral of dP, of course, is just P2 minus P1, or P minus P initial. P final minus P initial, I mean. So here we go. This is something that I can integrate, so I will integrate this. Kappa T, the problem said, can be considered a constant, so that's good. So ln V final over V initial is equal to minus kappa T times P final minus P initial. Okay, now Camille, notice in this problem, as it's shown in the problem, the equation that is shown in the problem, they use P and Pi. They don't call it P final, they just call it P. So I'm going to do the same thing. Instead of saying VF, I'm just going to say V. P is the thing that depends on whatever happens in the experiment, and so is V. Pi and Vi are the initial conditions that are constants. They don't depend on what happens in the experiment. They depend on how you or how the laboratory person set up the experiment. So we rewrite this using the same syntax as, the same language as the original problem here. Okay, now I can solve this for the V. The V is the thing that's changing, and the P is also the thing that's changing. But I need to solve it for the V because remember down here, there is a V that is changing with pressure, yellow. There is a V that is changing with pressure, and I need to substitute in here something that will give me a function of pressure instead of this changing V. So V, this changing V, I can solve for it now. Let me solve for it. To solve for V, I call this ln V minus ln Vi equals negative kappa T P minus Pi. And I better extend this. I might need some more space. Can you see this? Okay, I think you can see this. So my ln V equals minus kappa T P minus Pi plus ln Vi. All right. So now, I have to take the antilog of both sides. So I have to do e to the power of this side and e to the power of that side. But all right. So so this arithmetic, I think I've taken too many steps, but I'm going to end up with the same answer. Camille, when you do this by yourself on your own, you find a way to cut out a couple of these steps. Yeah. So, but it ends up being the same thing that I just. Okay, so here it is. So now Oops, I keep on accidentally maximizing. I don't want to maximize here. Okay, so e to the power of ln of anything is just that thing. So now this is v equals e to the power of negative kappa t p minus pi. Now, e to the power of two things added together is the same as e to the power of the first thing times e to the power of the second thing. Now, e to the power of ln v is just v. Oh, this is vi, right? Yeah, this is a vi there. All right, so v equals, so this thing is just v. Vi, I'm sorry, that's a vi. Vi times e to the power of negative kappa t p minus pi. Okay. So does that match what you need to see in the target equation? Well, there's an e to the power of something, and there's also an exponential thing. That means e to the power of course, in the problem. There's a kappa in the problem. There's a kappa here. And there's a p minus pi in the exponent, and there's a p minus pi in the exponent here too. So this is all good stuff. I'm going to substitute all of this in for the v. Okay? So let's do that. It's on a new page. I better pause here. Okay, so here's a new page, and commonly, are you familiar with the notation? E to the power of x is the same as saying this. People like to use exp because it's hard to put e to the power of x on a keyboard or something. I just prefer putting e to the power of x, but just remember that this means the same thing. Exp means exponential. All right, so get rid of that. Then continue with the work here. So that was I have found the v, and it's vi. It's this thing here. So I'll put that aside, and I need to let that be part of. Let that be substituted in for my expression here for delta h. At the bottom of your screen here, delta h equals 1 minus alpha t times the integral from pi to p of v dp. So I'll copy that over here. Delta h is equal to 1 minus alpha t times the integral from pi to p of v dp. Now, v was just, oops, where is it? V, where's the v? Where's my v? Where's my v? Where's my v? Is this it? Okay. Sorry, I'm going to find my v here. Okay, there it is. So v was just vi exponential minus kt p minus pi. So let's get back to the most recent page here. Here it is. So this equals 1 minus alpha t integral pi to p vi e to the power of negative kappa t p minus pi, and then there's a dp. Where did dp come from? At the bottom right of your screen, notice I was substituting in for v, and there was a dp at the end. All right, so let me circle in yellow what I just substituted in. I just substituted in this. Notice how what I circled in yellow matches what I circled in yellow at the bottom of your screen previously. This is from the previous page, just the v, right? Okay, so this is a very hard problem. I don't know how anybody could come up with the solution for this on their own. I mean, I certainly can't. Oh well, that's why I don't have a PhD right now. Okay, so vi is a constant because that's something that the experimenter controlled. The experimenter controlled the initial volume of all the initial conditions, so that vi can come out of the integral. And what stays in the integral is this, e to the power of minus kappa t p minus pi dp. So that stays in the integral. So what is the integral of all this stuff? Well, it's kind of nice that the integral of any exponential function is just the exponential function. There might be a chain rule issue for to do. And in this case, there is a chain rule issue to do here, but that's not too hard. All right, so as a review, oh, I just said that real fast, but as a review, let me do this. My favorite number somehow is 5. How weird that would be the case, huh? So if I wanted to integrate this, e to the 5x, the integral of e to the x dx is just e to the x, from your math class plus c. But that's if it's an indefinite integral. But anyways, the antiderivative of e to the x dx is just e to the x. So if there's a 5 here, then you have to do chain rule, right? Because integration is the opposite of derivation. So how do you do that? Well, if you put a 1/5 out here, if you put a 1/5 out here, and just to be fair, you put a 5 out here, so then 5 times 1/5 is just 1, so you haven't really done anything at all. By doing that, you make this integral easy to do, because the derivative of 5 times e to the 5x is just e to the 5x. I mean, the integral of 5 times e to the 5x dx is just e to the 5x. And then this 1/5 comes from there. Let me review that for you a little more carefully. So notice that if you have a function 5 times e to the 5x, and if you want, if you have a function e to the 5x, and you want to take the derivative of that function, if you want to take the derivative of this function, it is just e to the 5x and then the chain rule. The chain rule says if there's a function inside the function that you just derived, then you have to multiply the derivative by the derivative of that inside function. So here's the inside function. The derivative of that function is 5. The derivative of 5x is just 5. So the derivative of e to the 5x is just 5 times e to the 5x. So because of that, and because integration is just anti-derivation, when I have the integral of e to the 5x dx, I can't do it unless it's really the integral of 5e to the 5x dx. Why? Because the antiderivative of 5e to the 5x is easy. It's just e to the 5x, as we just saw in reverse. But in order to put the 5 here legally, I have to undo it out of the integral. So I could put the 5 there only if I put a 1/5 out here, because 1/5 times 5 is 1, meaning I've done nothing to the integral. So at the end, e to the 5x is the antiderivative of 5 times e to the 5x dx. So that's the answer to the integral here. But the real answer is 1/5 e to the 5x, because I couldn't have put the 5 there unless I had compensated by putting 1/5 out here. So the answer to the integral of e to the 5x dx is 1/5 e to the 5x. Okay? So in the same way, let's get rid of all this. In the same way, okay, so I'll have to delete this. Okay, so, okay. In the same way here, I'm going to solve this integral. Solving this integral, 1 minus alpha t vi. This is an I here, Kamala, sorry about that. This integral, to solve this integral, I have to take the derivative of what's in here, all right, and I have to multiply that here, okay, or in front, whatever you like. But in order to do that legally, I have to put 1 over that derivative here. So what is the derivative with respect to p? Because we are doing everything here with respect to p. What is the derivative with respect to p of this exponent which I have circled? The derivative is just negative kappa t, isn't it? Because there's no other coefficient on the p, and this pi is a constant, meaning the derivative of that is 0. So here, I'll do this in green here, so the derivative of that exponent is negative kappa t. So the reciprocal of that I have to put outside here to compensate for the fact that I'm about to put it inside is 1 over negative kappa t. All right, so do this step by step here. e to the minus kappa t p minus pi dp, and then here I'm multiplying a minus kappa t. Now the derivative of minus kappa t e to the minus kappa t p minus pi dp is just like we found the derivative of 5 e to the 5x dx. Alright, so this equals 1 minus alpha t times vi times 1 over negative kappa t, these constants I just copied down. And the derivative of, the integral of this is the antiderivative, which is just the integrand. What was, I don't really know what integrand means. What was inside the integral? Okay, so this thing that was inside the integral, this is being integrated from pi to p, from pi to p. All right. So next step is to substitute and to subtract. My favorite step in integration, because that's the easiest step. All right, so 1 minus alpha t doesn't affect anything. Sorry about that. Bi is a constant. This is also a constant. Kappa t. And then here we have e to the minus kappa t. Okay, so the p, I substitute the p in for p first, right? So it's p minus pi, and then minus e to the, you see what I'm doing? This is just the fundamental theorem of calculus, right? Integration. And then here, now I'm going to substitute the pi in for the p, right? Pi. All right. Oops. This had to be in black. Pi. All right. Okay. So this was the result of my integration, right? And because it was a definite integral from pi to p, I had to write this integration answer twice. I had to subtract it with the top variable p substituted in, minus the same thing with the bottom variable pi substituted in, right? But lucky for us, pi minus pi is 0. And everybody knows that anything to the power of 0 is just 1, right? So this whole thing, this whole second term, this is just 1. 1. I love 1. It's almost as good as 0. Okay, so now let me rewrite this to clean it up for you. I need a new page for that. Okay, here's a new page. So what I was dealing with, this was all delta H. All right, so back to the new page. New page, where are you? Okay, here you are. New page, delta H is equal to 1 minus alpha t vi minus kappa t e to the minus kappa t p minus pi. This is an exponent, all right? Minus 1. Okay, so that looks a lot like the original equation in the problem. All right, so let's see if we can get it even closer. Let's see if we can get it exactly. So delta H equals Vi 1 minus that. Okay, so in the original equation, this minus sign, I'll do this in orange, this minus sign is multiplied in there. All right, so I'll do that too. So that equals 1 minus alpha t, and in the original equation, the Vi is taken in front. That's okay because multiplication is commutative, right? And then kappa t is at the bottom. This is at the bottom, that's good. And now here I have, if I put minus 1 in there, then this is times minus 1, so this becomes a plus, and this is times minus 1, so this becomes negative. So it's really 1 minus e to the minus kappa t p minus pi. Okay, so that's it. There it is. Delta H, delta H, which means H, oh, okay, so I'll do this formally. All right, so delta H, which means H of P minus H of pi, or in other words, h of p final minus h of p initial, right, equals vi times 1 minus alpha t over kappa t times 1 minus e to the negative kappa t p minus pi. Oh gosh, that was so hard. All right, that's it. Call me if you have questions. No charge for calls after 9 p.m., right? I hope this works out for you. Sorry I can't meet you. Bye.